forgot to tell you one of the stories, and I like to tell them. You ready, Brian?
We're recording.
Okay. The back here, when people were using wood and skins and fibers and stuff, and stone, it turns out they actually did have an energy crisis. And the energy crisis, at least I'm sure they had several energy crises over the years, but the one I'm thinking of occurred about the mid-16th century in England. And it turns out the crisis was started out with two industries. One was people were starting to make iron, and in order to make iron, they needed a hotter source of carbon, or of fuel than just wood, so they would burn down the trees and they would make charcoal. Everybody knows how to make charcoal. You burn down the trees and you stack them up. You cut down the trees and you stack them up, and then you pile dirt over them, and you put a little hole in this kind of mound of dirt around there, and you control the amount of oxygen that gets in there, and you essentially ignite it. But in a reduced oxygen environment, and the whole thing heats up, and you have a hole at the top, and you basically burn off all the lignin and other stuff in the wood, and you end up with charcoal. And you need a charcoal in order to get a hotter fire, because when you have wood, the vapors coming off actually cool the fire down to a certain extent, all the lignin and these other things. But carbon burns hotter, and so they wanted charcoal. And they were using a lot of wood to make charcoal because iron was coming into greater prominence. And then another thing was national security. People were building ships. They needed wood to build ships back then. And so it turns out that it says as the iron industry grew, this is basically a history of metallurgy called Out of the Fiery Furnace. It's a PBS series. The forests of Britain had long been admired for their most celebrated inhabitants, slow-growing and long-lived. These were the mighty oaks. And it talks about the iron industry growing, and then the ships. It talks about Nelson's flagship at the Battle of Trafalgar took 2,100 tons of oak, thousands of trees, a whole forest, in order to build a ship like the Victory. So the two uses of oak were in conflict. In 1558, a law was passed forbidding the felling of trees to make coals for the burning of iron. But of course, the government exempted the areas that were important, typical government bureaucracy. You're not allowed to do it except for it's economically viable. But, and it says perhaps because of the lobbying by the iron industry. In 1559, a writer complained that the price had risen from a penny to 2 shillings. Does anyone know what that ratio is? I don't remember the old British system. It's like, I think it's a factor of 14 or something. By reason of the iron mills. By 1581, the shortage of wood for shipbuilding was so serious that a further act was passed forbidding the felling of trees within 22 miles of the Thames River, within 4 miles of the Great Forest, and within 3 miles of the coastline anywhere. By 1615, England was facing an energy crisis. Okay, and it turns out a third industry came along, which is glass making, which also needed hot fires and stuff. So it turns out that they had energy crises a number of times in history. And there's a case where the material you're using, the way to make new materials, were in conflict. Not unlike trying to make plastics and using the oil as our energy source today. But we were talking about selection of different materials, and I tried to point out that material selection is multifaceted. There's lots of different things you have to consider. Structural materials usage is strongly influenced by cost, which is probably the most important single facet. And steel is unique among all structural materials in combination of a number of these: strength, toughness, cost, fabricability, availability, the number of elements in the Earth's crust. The only thing that was above it was aluminum. And we'll start talking a little bit about aluminum today. We started to talk at the very end about the cost of material, or the application. I didn't tell you that because of this $200 a pound cost over the life of the vehicle, some commercial airlines require that a vice president sign off on anything that goes into the commercial airplanes. You know, like how many magazines you're allowed to carry on board. Think about it. You know, you got 50 pounds of magazines. That just cost the company $10,000 over the life of the aircraft at $200 a pound. Okay, so you don't always stop to think about it. I think about it every time I see magazines on the aircraft. I think, whoa. Anyway, we talked about the X-33 space plane, which was supposed to replace the space shuttle. I think in other parts of the video, when I talk about adhesive bonding, I'll talk about this, but it was towards the end of the day, and I didn't pass this around. This is a graphite epoxy composite skin and a Nomex or Kevlar honeycomb, and you've got a foam composite between these two sheets, and you've got sheet adhesive in between here. What happened is when they went to make this, it was in the early 80s, or early 90s, and they just had the Gulf War. And it turns out that the Defense Department was really big on what they called rapid prototyping back then. If you've heard of 3D printing, something invented by Professor Seaman down here in the basement, with Professor Sachs over mechanical engineering. But they wanted to be able to build things, special types of military equipment that you could take into war within 2 weeks, or things like that. So NASA got involved, and they wanted to build this thing within 33 months. Okay, the prototype, full size, actually half-size vehicle, but I mean it's as big as a fair-sized plane, because the actual one would be the size of about the size of the space shuttle itself. And they awarded the contract and to Lockheed Martin, and it turns out Lockheed Martin, the people who build the space shuttle down in Mississippi, the space shuttle main tanks, refused to bid on it. They said you couldn't do it in 33 months. So Lockheed Martin's management gave it to the Skunk Works, because the Skunk Works will do anything, right? You can do anything, supposedly. And it turns out, as they were in a rush to go from clean sheet of paper design to first flight in 33 months, they just were trying to take things off the shelf. That honeycomb you can buy off the shelf, okay? And the graphite fiber epoxy you can buy off the shelf. They needed an adhesive to bond it together, so they looked on the 3M website. I don't know if they had a website back then. I guess they didn't back then. Anyway, they got some information from 3M, and it turns out it was a structural adhesive for aluminum. And the bullet point said that it had a shelf life of 10 days before you put it in the autoclave. The autoclave is where you heat the whole thing up to cure the adhesive. You heat up to about 300 degrees Fahrenheit to cure the adhesive. And you actually store these sheets of adhesive in a refrigerator, because you basically, it's an epoxy that wants to chemically react. And so they said 10-day shelf life out of the refrigerator. And so they said, great, that'll work. It'll only take us somewhere about 4 to 5 days to lay up all this composite, and then we can put it into the world's largest autoclave, which we have available in Sunnyvale, California. And what they didn't realize, because it was just bullet points, that the strength of the adhesive versus days, going from 1 to 10, looked something like this. And it had about 10% of its original strength after 10 days. And they were right in here. And they thought, by the bullet points, they were up here in strength, right? So it turns out, when they actually made it, they had about half the strength they thought of. They sharpened their pencils, and they said, well, we still got a 5% safety factor. Let's test it anyway. So they put it in test, and the thing blew apart. So they canceled a $1.3 billion program. But just kind of material selection by bullet point.
What was driving that 33 months, 31 months?
Some guy saying 33 months. Okay. It's sort of like I had a student, LFM student working at GM once, and they were going to start building a Chevy Cavalier in Cleveland, which is a number of years ago. This is the current Cavalier, but this was like 10 years ago. They said that to put it into the Cleveland plant, and they said that they were going to have no more than 2 hours of inventory, because they're going to have just in time. They were going to do the Toyota production system, right? They're going to have no more than 2 hours of inventory for any part. Well, you know, you can have a week's worth of bolts in a little box this big, right? But no, you know, some manager put a blanket, you know, no more than 2 hours of inventory. So they actually had to take the bolts out of the big thing and put them in little things, and now you have to transport the little things every 2 hours, right? You know, if you were talking, you know, panels, you know, that, you know, would take a football field for a week's worth of inventory, okay, you only want 2 hours of inventory, but for bolts, you know, it was just insane, you know. So it's, you know, it's management by objective, right? Stupidity by objective. Yes? No, sorry. Yes. So there, I don't know that there was anything other than some guy decided that's how long it's going to be. You know, maybe it had to do with congressional appropriation timescales or something, I don't know. Okay, so that's the X33. It turns out steel is not wonderful for everything. As you go faster and faster, you'd like to have something that's less and less dense. However, sometimes we forget that if something doesn't move, you don't really care about what it weighs. You care about what it costs. However, if it does move, you do care about what it costs, because the heavier it is, the more it costs to move it. Okay? Just more energy. And in fact, the faster it moves, the more you're willing to pay to get lightweight. And so if I went back to that cost of $200 average savings on a commercial airplane, if you look at military aircraft, it turns out they figure about $1,000 a pound. And that's $1,000 a pound on the average structure. If you actually start talking about on the rotor disc, which is spinning at 10,000 RPM, you're willing to pay tens of thousands of dollars to get rid of a pound, because a pound saved there might result in 5 pounds saving on the wing. Okay? So if you and you move faster and more payload and or further distance, people will pay a lot. I remember when the almost 20 years ago, 15 years ago now, I had just come back from Japan, 2 weeks in Japan, and I got a call from Engelhard Company. And Engelhard was making catalytic converters. These are catalytic converters, I passed them around last time. For 747s. They were coming out with 747-400 at Boeing, and this was going to be the long distance 747-400. In order to take weight out, they didn't want to make, did you know there were a couple of catalytic converters on 747? It's not for the engines, it's for the air you breathe, because there's ozone up there. And you would get a headache if you were breathing the ozone. So they have to take the air up there and put it through a catalytic converter to get rid of the ozone in the air, so that you won't get a headache when you're, and you will meet EPA regs for quality of air when you're up there. But they have a couple of catalytic converters. And all the piping had been made in the earlier 747 out of stainless steel. They were now making it out of titanium, and they didn't know how to weld it. Okay, so I didn't know how to weld it. There are other reasons why you pick different materials. I gave this as an example of a ceramic for a catalytic converter last time. And this actually is a design for an automobile. This actually is also a similar design, but this one's made out of a very high grade of stainless steel. And it's not really fair to weigh them because this one doesn't have a shell on it. But even so, it's not necessarily this one is lighter. It's not because it goes faster, but you want it to heat up quick. Because it turns out catalytic converters, once they get hot, they don't work until they're about 1,000 degrees. And so when you first turn on your car, you're spewing out all kinds of emissions until the catalytic converter warms up. Once it warms up, it's pretty good, and you don't really have a whole lot of emissions. Okay, you got to warm up your car before you take it in for the test. You know, the environmental, your sticker. And so you want to pass these around. This was designed because they got ever-increasing environmental restrictions, and they were looking at a material that instead of taking 10 or 15 minutes to warm up and start working, could start working within a minute. Because right now, about almost 100% of your emissions occur when you first start the car in the first 10 minutes. So lots of short trips, catalytic converters not doing that much good. Long trips, those vehicles have very, very low emissions. So in that case, the heat capacity or low heat capacity of the total assembly is good for rapid heat up things. So lots of different criteria. There was a guy who was head of materials at GE Aircraft Engines named Bob Sprague, who probably retired 10, 15 years ago. And another guy, Jim Williams, who retired or went to Ohio State replaced him and then went to Ohio State about 10 years ago. But Sprague's first law says that, okay, so Sprague's first law, whenever you hear something about a new material, write it down because that'll be the best thing you ever hear about this material. Okay? New materials are wonderful when they're first invented. And Jim Williams' corollary, he replaced Sprague. When you first hear about the price of a new material, write it down because that'll be the lowest price one over here. And actually, Jim and I both gave a talk once at a conference. We both ended up saying basically the same thing. Cost was the important thing in selection of new materials. Jim called a lot of the advanced materials that people tout, called them boutique materials. Because they have very, very limited application. However, I remember when he was an academic at Carnegie Mellon, dean of Carnegie Mellon, he used to tout the new materials just like all the other academics. Anyway. I also handed out this thing, which is an appendix that I wrote for this National Academy report. And a lot of it is basically the stuff that I've been talking about. And in this handout from yesterday, I had this graph, this graph goes back to 1962. A guy named Jack Westbrook, who was an engineer at General Electric, doing some strategic planning, and he plotted the pounds of material use per year on this log scale. We're going over 10 to the 4th to 10 to the 12th. And we used 10 to the 12th pounds of stone in 1962. And the dollars per pound going from less than a cent a pound up to $10,000 a pound over here for diamond. And you don't use a lot of pounds of diamond, maybe only 5 tons a year back then. You do use a lot of stone, but it doesn't cost very much. And you can see that on this log scale, that's not a bad relationship. For structural materials, this is structural materials, not functional materials. It turns out steel is right here, cement's right here, super alloys, these turbine blades. I passed around a turbine blade. In fact, I have another turbine blade we can pass around today. This is a cool turbine blade, but it has a ceramic coating on it. Okay, that ceramic coating has been put down. It takes a couple hours and a $15 million electron beam unit to lay down that ceramic coating. A lot of technology in that. But they're way down here, and the dollars per pound back then was probably 5 or 6. Today, the dollars per pound is probably $30 a pound for that material before you do the casting. In any case, there's another line on here, and this is the ISO market line, these dashed lines. And the interesting thing is the trend line has a slope that's about 4 times steeper than the ISO market size line. And what that says is if you cut the price of your material by a factor of 2, in the long run, you should quadruple the sales. I'm not going to do it overnight. But materials will find applications. If you reduce the cost of the material, you'll find more applications for the material. And in fact, in the long run, your market should expand because the trend line for usage exceeds has a steeper slope than the ISO market size line. That's my prediction. Actually, there's a study, but I bet you did a study to prove it. All I have is probably some anecdotal stuff. Now it turns out, and this is in a little more expanded scale in that paper I just mentioned that we handed out yesterday. It turns out most material scientists will tell you how wonderful the material is and how the cost of the material is such an important part of the whole thing. Turns out it's not. And that's why this is a welding joining fabrication course. Because the cost of the material, typically, for most things, manufactured products we're interested in, the cost of the material is only about 10% of the total cost of the product you're going to sell. You got about 10% of your cost will be design, about 10% will be materials, about 10 or 20% will be fabrication, about 10 or 20% will be non-destructive evaluation of the material, testing, quality control. Hopefully you got 10% profit. Anyway, the numbers are in a little table. The expanded numbers are in a little table that I put together in there. The one application that I know uses more material as a fraction of the final completed product than anything else is pipeline. And the cost of the pipe is about 30% of the cost of the pipeline. Although you could argue that I should have started with the cost of the plate rather than the cost of the pipe, in which case that number would come down a lot closer to 10%. Okay? Because the pipe costs about close to 3 times as much as the steel plate. One of the reasons is because when you ship pipe, you're shipping air. Okay? So it costs a lot more to transport pipe aside from just the manufacturing cost. And in fact, I learned a number of years ago, actually, it ended up becoming an elephant project. It started out as a consulting project, but we ended up selling this company, Reading Tube. It's a copper tube extrusion plant. It had a couple of elephant theses done there. And it turns out the United States still has 5 producers of copper pipe. And the reason is, copper pipe's not like steel. Steel, they load on ships and they transport it around the world. Copper pipe is even more valuable, and so you'd say, well, gee, why? Or copper is more valuable than steel. How come it's not traded as a commodity? Well, it turns out copper pipe has got a lot of air. Okay, and so you can't transport it as efficiently as you can big blocks and big plates and sheets of steel that are all rolled up and things. Pipe, by its nature, is 80–90% air. And it turns out the transportation costs are the things that control that selection of material. You can say the same thing about cement. Although they trade cement around the world on ships, there's still plenty of cement plants and cement manufacturing facilities in every country because basically you can't afford to transport cement more than about 300 miles unless it's by water. Okay? If it's over land, you can't go more than 300 miles. So if you want to get in the cement business, you ought to look and see how many other places make cement. Because the price of cement is so low, you can't afford to transport it very far. So, whereas diamonds, they put them on a plane, but who cares about the transportation cost? Semiconductors, which are functional materials, or spacecraft, which are in a world of their own, literally, don't necessarily follow those kind of transportation and fraction of the cost rules. If you start thinking about those fraction of the cost rules, and this is also in that handout, and you go back, this actually comes out of Ashby's book that we talked about yesterday. And this is per ton, so diamonds are about $1 billion a ton back then. This is 1980, but it doesn't really matter. If we're talking about an automobile where the price of the material shouldn't be more than, let's say, 20% of the fabricated cost of the product, and you can only, the structural material is only worth about $2 a pound over the life of the vehicle, that means I shouldn't be paying more than 40 cents a pound for my raw material to make an automobile. This is pretty simplistic because I'm a pretty simplistic guy. But it turns out that means these are your choices of materials to make automobiles out of. Polyethylene, probably not a good choice, not very strong. Okay, silicon carbide, probably hard to machine. Plywood, well, they used to, okay, the old woodies, right? Low alloy steel, mild steel, cast iron, concrete, coal, and cement, maybe some of these others are a little heavy. But why do we make cars out of steel? Because at $2 a pound gasoline, which is what, not $2 a gallon gasoline, and everybody wants to sell in the United States, they make cars out of steel. If we were talking about, we got up here to aluminum sheet, and we were willing to pay 80 cents a pound for the raw material to make the car, or we were paying $4 a gallon for gasoline, assuming that oil still costs us $30 a barrel, okay? Then you can make a car out of aluminum. Well, much of Europe it already was at that price for a gallon of gasoline. But the people in Europe want to sell their cars in the United States, so they design them out of steel. Okay? But economically, it would make sense to have all aluminum vehicles as the only type of vehicle in Europe. Yeah.
Quick question based on that line graph. This might be a dumb question, but what's the difference between concrete and cement?
Oh, concrete is the composite that you take the dry cement, which is the powder in the bag, if you will. Cement is what you calcine. You dig the rock out of the ground, and you drive off the CO2 out of the carbonate, and you end up with this powder. Okay. If you just take cement with a little bit of sand, you call it mortar, and you mix it with water, you call it mortar. If you mix it with rock and stone and all kinds of other stuff, you call it concrete. Okay. So the pavement is concrete. We sometimes call it a cement-wide sidewalk. It's concrete made out of cement. Okay. In between the bricks, it's mortar made out of cement. I happen to know this because my father worked in the cement business. Anyway, but there is a difference, in fact. But cement is what you make. You make concrete out of cement with rock and stone and other things in it. Okay. And in fact, concrete has become the solution to every environmentalist problem. Okay. Because you're going to bury it in the concrete. Now they said, well, we got certain types of plastics we didn't know how to recycle. This was 15 years ago. They said, oh, we'll just grind them up and we'll use it as aggregate in concrete and pave the roads with it. Well, you know, everybody was going to dump everything in concrete, and we don't use that much concrete. Okay. Anyway, this is the line. Below here is cars. Below this line are things you can make a commercial aircraft out of. And above that line are the types of things that you can start thinking about spacecraft. That's where I drew those lines on there. Okay. Anyway, that's this same type of thing as in the handout. Let's take a little bit more time looking at Ashby's types of plots. And if you're taking a very high-level view, these are very, very useful plots. Ashby actually goes through some engineering mechanics formulas and says these are guidelines for minimum cost design, and he says basically strength divided by density, but the strength in some cases should be the 1/2 power or the 1/3 power depending on the shape, the geometry, or the application. And he actually goes through certain types of things, whether you're using them in sheets or whether you're using them in a bulk material or whatever. And so you can kind of overlay on this thing. You can look at different regions depending on these slopes of comparing materials. For example, if you're on this steepest line, something here, silicon carbide, you come down that line and say, well, silicones may not have the strength, but on a relative cost, they have the same quality, okay, or actually attribute, J or whatever Professor Clark calls it. Yes, so ceramics are the hardest, strongest materials, but they're brittle. Metals are used widely in structural materials because they're not brittle, which is another dimension of toughness, which isn't on here. But they have high strength and at a fair cost compared to these things. However, if you look at that, these lines, there's a lot of trade-offs on all these materials. We use plastics for structural materials. Okay? This is cost per unit volume, so the plastics have done a little better because they're light, okay, even though they're weaker on an absolute scale. But that, for a structural material, you usually are looking at cost per unit volume. I did find my toughness plot, which I got the wrong one yesterday. There's lots of different criteria on these slopes over here. The engineering alloys, these are the metals. These are your, is that tungsten alloy? Anyway, tungsten carbide, cobalt, aluminum alloys, I can't read titanium alloys, cast irons. Down here, your polymer foams are very, very light, but and don't have such great toughness. But if you're talking about ultimate toughness, the engineering alloys, the metals, are way out here, way above anything else. It's just metals have ductility; they stretch before they break. And it turns out people can come in and talk about other wonderful things, but they just can't compare. And this is the one I put up before. This is modular stiffness. Sometimes stiffness becomes the criteria. For example, as you're doing microsurgery, you know, when I was your age, I tore when I was younger than you, I tore the cartilage in my knee. And at that time, to fix the cartilage in your knee, which I never had done, it was like 6 months on crutches afterwards because they had to lay open your whole knee. Nowadays, they just put a little slit in there and they go into these little micro tools and fiber optics and stuff, and they can go in there and eat out the little rongeurs that can eat out the cartilage and flow it out of there. But it turns out as you do that, you get the slender and slenderer instruments. So you get slender and slender, and they get a little too flexible. And so I actually used to work with a division of Johnson & Johnson, and they wanted to know, our instruments, we can design them smaller, but they're too flimsy for this application. What do we do? Well, they were already using steel, and it turns out steel has got about a 30 million modulus. It's right up in here somewhere. Can't read it on this thing. Steels. Okay, there's steels right there. It's way up near the top. It has relative low cost, but it's why right up near the top. There's not a whole lot of things above it. Aluminum oxide, silicon carbide, diamond, okay, molybdenum alloys. It says tungsten alloys right there, but molybdenum's up there a little bit above it too. There's very few things that have a higher Young's modulus, which is what you need for a bending beam. Okay. However, I did recommend to them that they consider using sapphire, which is single crystal aluminum oxide, because you could add dopants to it, things like chromium, and you can make it red, so it can be color-coded. Physicians like color-coded instruments. It has excellent corrosion resistance. And it turns out single crystal sapphire is now down around a few bucks a pound. Now, it's a little hard to machine, okay, because it's second hardest to diamond. You can only machine it with diamond tools. But I actually thought we could design little cutting tools, and they're hard, you know, but they never liked that idea. But it is stiff. You could have designed smaller tools. And if you did add chromium, the sapphire is no longer sapphire, it's something called ruby. And can you imagine going to an MD and selling him, we're going to sell you, you can either buy the sapphire instrument or the ruby instrument. And MDs, you know, they're like offers, they buy anything. Anyway. Specific strength. If we start looking at strength for divided by density, it turns out aluminum is better than steel. That's one of the reasons for using it in many applications. If you think of an aircraft, it's made out of aluminum. There's a good reason for it. It's got better specific strength. You can afford to pay for it because it's more, you know, you can pay more than $2 a pound for the aircraft. Simple composites, and I mean things like fiberglass. I'm not talking some aerospace composite, okay? If you talk, well, let's just say simple composites. Plastics really kind of bite the dust. They're not very good on strength-to-weight ratio. They are good when you really don't need a lot of strength. They're great. And wood, you know, is not as good as some of these other things. So there's lots of different criteria you can use, and you have to figure out which one for which specific application. What was I going to say about the? Oh, turns out I'm designing a new aircraft. I remember someone from Boeing said that you start with the landing gear by designing the landing gear. You have to estimate what you think the whole plane's going to weigh, and you can do that from trend lines. So, you know, you built different size planes before, and you know what size plane, you like to build, and then therefore you know what weight it is, and so you design the landing gear, because the landing gear is the most highly stressed application on the aircraft. So you make it out of the best steels in the world, 300 KSI steels, and you're willing to take the weight penalty for the landing gear because there is nothing else that has the strength, toughness, performance, except some cobalt alloys that will cost you a fortune and weigh just as much. Okay. And once you design the landing gear, well, then you can design the keel beam. An aluminum, an aircraft, actually, a big commercial aircraft, has a keel beam just like a ship. Okay. In fact, TW-800, the one that split apart over Long Island, I was under there looking at the original fracture in the keel beam because they had an explosion in the gas tank, and it just split, just broke the keel beam. It's like breaking the back of the ship, split it too. Anyway, if you consider high volume applications, you got to worry about cost. And here is strength to weight, so approximate cost per pound per dollar. So steel has a 6-fold advantage over aluminum. So if I'm building a bridge that doesn't move, steel. Okay? If I'm building an aircraft, hey, I can afford aluminum because it's $200 a pound and $1.20 doesn't bother me at all. So there's lots of different criteria, and people come up with these different figures of merit. Now, so the next part of the talk, which I don't know if I need to go through, but since we got a lot of LFM students here.
Sorry. What about comparing just with steel and aluminum? Shouldn't just durability, but it's a fatigue characteristic? Doesn't that really play a big role in what you design to? Or?
Yeah, it does, but steel actually has better fatigue characteristics
Right.
than aluminum. Okay. However, clever design, clever mechanical and geometric design can solve, or inspection can solve those things. If you can get a better performance, and I don't want to build steel aircraft, although you actually can. The small aircraft, if you wanted to go build a little, home-built aircraft, with a small engine, a little 4-cylinder engine that's going to go 125 miles an hour and just go, so you can go up in the air on nice days and stuff. Typically, they make that out of a steel space frame structure. It's just steel tubing. It's easy to weld. It's relatively light when you just make a space frame structure. And then you cover it with fabric, typically. And this is not all that different than what they built in the 1920s. Okay? And in that case, the steel actually has better fatigue resistance, and all you have to do is keep it from corroding. Okay? Aluminum, if you're building and you're going to pay for lots of gas, which is the big driver or jet fuel is the big driver for the commercial airlines right now, the cost of fuel, is you want to have something that's going to be as fuel efficient as possible, and so you're willing to spend the time with good mechanics doing the inspections on the aluminum to find the cracks. So yeah, aluminum will crack more readily than steel, but it's something we've learned to solve, okay, by inspection. It's a maintenance cost down the road.
Right.
That you're willing to pay more capital and more maintenance because it has such lightweight, okay, such a benefit in the beginning. So these things become very complex things on how it's not a simple trade-off. There's no simple answers in this, which is why us material scientists still have jobs.
What are your thoughts on Boeing 787 and using a composite there? We were out there for a plant tour and we saw them building spooling around.
Well, composites have come a long way since people quit thinking about high-performance composites. In fact, one of my favorite stories is Professor Gutowski over in mechanical engineering made his tenure in his career in the 1980s. He's a few years younger than me, but basically he was tenured by 1989 when LFM started. And he got his tenure by looking at high-performance composites. In the very first year of LFM class, he supervised a couple of students out of Boeing. And he came back, he now works in environmental areas rather than high-tech composites. But he came back after supervising the students that first year and saying, we don't need better composites. I mean, he'd been working in the area for 10 years, right? He achieved tenure. He was a full professor. He came back and says, we don't need better composites. We need cheaper composites. That's what the engineers at Boeing had instructed this academic, okay? I remember about that same time, Professor Clark of this department published a paper in Journal of Metals about relative cost of materials. And I was walking across campus with Professor Chang. I was actually going over to LFM. And we were walking across, and he says, he said, did you see Professor Clark's article in Journal of Metals? I said, yeah. He says, you know, I hadn't thought about it before. Cost really is important. Okay? Well, this is kind of the epitome of engineering faculty in the United States. Okay? These are full professors at MIT, okay, one in materials and one in mechanics, and they didn't realize the cost was the object out there in industry. Okay? I can tell you another story. When I became department head in 1995, and I've been LFM co-director, and said, you know, we really ought to learn more about what industry is really doing in manufacturing. For example, how many people here know what a CPK is? None of the faculty in the room, in the material science department, raised their hand. They didn't know what the quality, you know, all of you know what CPK is? Anybody not know what a CPK is? I guess that's just embarrassing. A CPK is a quality metric for your process capability, okay? Basically, you have a lower limit of your process tolerance and an upper limit. And you should have some Gaussian distribution. You want to know if your Gaussian distribution, if you're going to produce good products most of the time, or your Gaussian distribution is broader than your limits. Okay, so CPK is a simple number. If you have a lower control limit and an upper control limit, you'd like to have a Gaussian distribution of your process variation where virtually everything falls between your process limits. Okay, you don't want something where this is scrap and this is scrap. Okay, so CPK is a measure, a mathematical measure of the width of the Gaussian to the width of the process limits. And it's got to be at Ford, it's got to be like 2.7. I mean, if you're going to sell something to Ford, you have to tell them what your CPK is of making that switch. Okay? And if you're below a certain level, you could be cut off. Okay? That's the way business worked in the early 90s. But the engineering faculty at the universities were clueless. Absolutely clueless. Okay? But since we're on that, since I like to do sides. So it turns out in the early 90s, the CEOs of AT&T and Kodak and IBM and Boeing, lots of big companies got together and said, we've embraced total quality management, and we know what it is. No one at the universities understand this. And so we are going to offer up our in-house training facilities to take 50 faculty from from actually selected universities, not any university, Stanford, MIT, University of Illinois, I don't remember all the universities involved, but MIT was one of them. And we will give you our full course on TQM so that you can go back and teach the students. Well, I had already taken Professor Shiva's course at LFM, okay, and Shiva doesn't teach anymore, but he wrote TQM handbook and stuff. And it turns out Alex Darbeloff, who used to be the MIT chairman, wrote some of that with Shiva and taught these courses with Shiva. So you had CEOs saying, you know, quality is important. We learned that from the Japanese in the 1980s, okay? So it wasn't as if American industry really understood this back in the 70s and 80s. But they learned it in the 90s, and so they thought they should teach it to the university. So it turns out IBM got MIT, and so 75 MIT faculty, they upped it because there's so many faculty at MIT who wanted to go do this. We all went out to the IBM training facility on the Hudson. Okay, this is on the west side, it's not the Poughkeepsie side, but it's not too far away. Beautiful facility. And we were there for a whole week, 75 of us. And Chuck Vest, the president of MIT at the time, came out and gave one of the welcoming speeches. And we had a senior executive VP from IBM, and he gets up to talk about what IBM called their total quality management. They had a different acronym. They called it customer-driven quality, CDQ. And he got up and he says, you know, at IBM we've gone from 410,000 employees to 320,000 employees with no loss of direct labor. So it's all overhead people, right? And he says, we used to have 90,000 people in there to keep problems from rising to the top. And by going to CDQ, we have reduced our workforce by almost 25%, right? And so afterwards, people asked questions, and I was 5th or 6th. I said, by the way, you used to have 90,000 people in place trying to keep you from having problems rising to the top. Now that you've gotten rid of all those people, have you seen more problems rising to the top? And he stops and he thinks, he says, well, no, we've actually seen fewer. So they had 90,000 people with negative value added at IBM. However, they got there, and through the whole week, it was very interesting because they started telling us about house of quality. Well, who had invented house of quality but Don Clausing of who had been at Xerox, but he was now at MIT in mechanical engineering, and he was sitting in the audience. And so he had people at IBM who had learned about house of quality teaching him what it was. And I can't remember, Professor Sturman and Sloan, can't remember what, something that he had invented. They were teaching us, and John Sturman was sitting right there. At some point, I think some of us pointed out that maybe you guys ought to think about who you're teaching. Because a lot of the stuff actually had been invented at MIT, but never, or by people who were currently at MIT. However, most of the rest of the faculty at MIT are still students, even today. Okay? They don't know what a CPK is. Actually, I think it's improved. Since 1995, when I became department head, when Joel Clark and I were probably only 2 out of 35 in this department, we could tell you what a CPK was. There might be 4 or 5 out of 35 now. Okay? So we're, another 30 years, we'll be there. And a lot of the quality stuff we talk about, a lot of it was developed by AT&T. When it's called Bell Laboratories, not Bell Laboratories, Bell Telephone System, in 1925. Okay? And all these wonderful things that Japan had, where did they come from? They started with Edwards Deming. Okay? Edwards Deming worked up here at Nashua Corporation. No one else in the United States would pay any attention to them, so we went over to Japan. Nashua paid some attention to them. Of course, they lost all their stuff anyway. Any questions? This is not a digression. How much time do we have left? We don't have, well, okay. The time we have left, let me tell you the story about what happens when an industry is faced with extinction and how they can really significantly improve. And I'm going to show you, this is 1980 data for the U.S. steel industry. And this is employment dropped by 50%. Okay, from 550,000 to 275,000 in 10 years. And if you were around in the 1980s and even the 90s, everybody was talking about steel was a dying industry in the United States. And then you'd look at shipments, and it was constant. Forget this dip in 1982, but it's constant, 75 million tons. Okay, we actually use about 100 million tons, and we have for about 30 years, but the rest of them were imports. This was the recession of 82, and it took a while to come back up. Well, let me ask you, if you have constant output, but employment goes down by a factor of 2, what happened to productivity? It went up by a factor of 2. Duh. Okay, here's productivity, went up by a factor of 2. That's double the rate of all other U.S. manufacturing in the 1980s. But steel was the dying industry. They went from, it turns out between 1980 and 1995, manufacturing of steel went from 6 person hours a ton to 1 person hour a ton. Today, it's below a half a person hour per ton. Okay?
Are the production levels the same still?
Yep. You go into a steel plant, a whole steel plant used to have thousands of people, now has hundreds of people.
Yeah, that's my dad's in the steel industry.
Yeah.
And he worked for a plant that closed down, had 1,500 people, and he went to go work for a plant that had 300 people, and only 150 of those actually worked on the floor, and they put out actually more steel than the previous plant.
Yeah, I mean, and it turns out you ended up bimodal. You had the old fogies who, the Bethlehems and the U.S. Steels who were not going to change, and then you had these little mini mills who were these guys who had been at those other companies and said, this management is for the birds, and they went off and did it right, okay? And they were making money for a while, but anyway.
It was kind of creepy. I go out, I took a tour of the new mill that he's at, and there's no people there.
Yeah.
There's not anybody on the floor, and I was used to it. I had taken tours of the other big mills.
Yeah.
There's thousands of people on the floor.
Well, in the United States, I used to be the POSCO professor, so I visited POSCO the year they became the world's largest steel company and had the world's largest steel mill in Pohang, Korea. And you drive through there, and you don't see anybody. This is the world's largest steel plant. You hardly see anybody except a couple of carts on the road or trucks on the road. You look in the plants, and they're empty. the steel's going through by thousands of tons. I mean, it's really amazing. You have a question?
I was just wondering where the steel is being produced these days, because I was under the impression Bethlehem and Pittsburgh weren't producing a whole lot.
Well, Bethlehem is bankrupt and been sold several times. Just bought by IRG, which is a conglomerate. I guess the simple answer is, well, it's not that simple an answer. After World War II, the United States made 75% of the world's steel because we had bombed out the rest of the capacity. When I worked for Bethlehem Steel in 1974, which was 1973 was their most profitable year ever at Bethlehem Steel, they made 25. The United States made 25% of the world's steel. Today we make less than 10% of the world's steel, about 8% or so. What happened is the last greenfield integrated steel plant ever built by a company was built by Bethlehem Steel in 1965 through 1970 in Burns Harbor, Indiana. It cost $5 billion at the time. In the mid-60s, $5 billion was real money. Bethlehem almost went bankrupt in the 60s for this huge capital investment. This is kind of like Boeing says, well, it's going to cost us $30 billion for the next airplane. Well, this $5 billion for Bethlehem was like $30 billion today. Okay? How many private companies can bite that type of apple, right? Bethlehem did, and as a result of the Burns Harbor plant, by 1973 was the most profitable year ever, even though they were almost bankrupt in 1968. Okay. The problem was the management at Bethlehem when I was there still had the mentality that we control 75% of the world's steel output, because that's when they were hired in 1946, and they still had that stupidity in their minds. And they didn't see the trend going. Now, since then, no single company has built an integrated steel plant, which I estimate about $15 billion today. Only countries have built integrated steel plants. And in fact, many countries have built integrated steel plants because steel is sort of like oil. It's essential to your economic well-being. And so countries will invest and build an integrated steel plant. That's how POSCO came into being. U.S. Steel built the plant for them because the government of Korea, the Prime Minister of Korea, who was a general, told Colonel Park, who was his attaché before he became president, he says, "You're now president of our steel company." They had no steel company. And Park went to U.S. Steel and says, "Will you build me a plant in Pohang?" Okay? So the government of Korea built POSCO Steel, which is now the world's largest steel company. Saudi Arabia built a steel plant. They're using natural gas, which they're just flaring off otherwise by a different process, to make steel because it's fundamental to the economy. Everybody makes steel. As a result, in the 1990s, there was a huge overcapacity. The steel plants, the world only needed like 70% of the capacity, and most people in the United States had an 85% capacity break even. That's why they were losing their shirts. However, their productivity was going through the roof. What industry had a higher productivity? The American steel industry in the 1980s had double the productivity growth of all the rest of American manufacturing. If I take manufacturing out of the equation, the United States as a country had near zero productivity over the 1980s. That's in the service sector, right? That everybody was saying, oh, it's wonderful, the service sector, right? Investment banking. Zero productivity growth in the 1980s. Average of U.S. manufacturing was about 2% over that period, 2.5%. Steel was 4 or 5%. What industry had 6%? Mining, which is even more maligned than steel making. Why? Because the threat of extinction causes a company to be willing to take the risk that are necessary to improve yourself. If you don't, you're going to die. So, necessity's the mother of invention, however you want to say it. But, those are real numbers. I've given this talk in Washington and actually testified before Congress about it. But, it's pretty amazing if you actually look and see. There's a lot of innovation. They don't make any money, and so Wall Street hates them, and all the newspapers degrade them, but they actually are some of the most innovative manufacturers in the United States. So, anyway. Give no respect.